Okay, so for question 1, the scenario is as follows. You've got Gerald who's throwing a ball horizontally and it's going to plummet to the ground like so. And then you have Omar who's dropping an identical ball that's just going to fall straight down. And the question's asking why do they both actually land on the floor at the same time? So the 4 marks that you're going to be looking for here is first of all, you want to talk about that the time taken is going to depend only on the vertical component of the velocity. And from that, you can talk about how the vertical component of that velocity in both cases is equal to 0. How does it depend on it? Well, it depends on the acceleration, which will change that vertical component. And the acceleration in the vertical direction is 9.8 meters per second squared for both of them. In fact, it doesn't really matter what it is, as long as it's the same for both of them. And the final mark is to talk about what equation you would use. Personally, I would go with S equals ut plus half at squared, because then you can point out that the distance is going to be the same, and if the distance is the same, the vertical velocity is the same, and the vertical acceleration is the same, then t must be the same. Alternatively, the answer key also says that you can use v equals u plus at. Right, so in question 2, you've got your standard inclined plane problem. So the first thing it's asking you to do is to sketch and label the forces acting on the stationary car. So let's go ahead and do that. So you've got a force acting downwards, and that one is going to be weight. Otherwise, it's mg. Now you're going to have a reaction force coming perpendicular to this plane, the normal force. Of course, you'd use a ruler. We'll call that the normal, or the reaction. And you'll end up with a force going this way, and this one would just be friction. Now, it doesn't ask you to do so, but the next thing I would do is I would actually make sure that we understand that this car has no net force acting on it. So really what you should find is that the weight force, which is coming down, should be made up, well, should contribute to these two, your friction, your weight, and your normal force. Now the reason that's important is for the next step, because with this triangle that we've just drawn, we know that this angle here is going to be 25 degrees. So with that in mind, it says here, calculate the force needed to stop the car from moving. In other words, calculate what F is. So if we have sine 25, your opposite over your adjacent, hypotenuse, sorry, you should have F equals weight 25 is equal to mg sine 25, and it should end up with my calculator got 6380 newtons, or if you want to be good, 6.38 times 10 to the 3 newtons, and there's your answer. So you've got, it's worth what, 5 marks. You've probably got a mark for the arrows, a mark for the labels, probably 2 marks for the labels actually, and then you're going to end up one with the calculation here and then another here, but it depends on the marker. Okay, this is a nice and easy equilibrium problem. So you've got a situation where you've got a castle wall with a rope, so you're going to have a force acting in this direction, which is going to be a tension, and you've also got this drawbridge. So you should have at the center of mass, so if this is 8 meters long, which it is, I think, yep, 8 meters, so that means at 4 meters you're going to have mg acting downwards. So you've got the mg acting downwards, you've got the tension acting opposite, and that's all you should have. So from that point on, you can have your sum of your clockwise. It's got to be equal to your sum of your anti-clockwise. Most important bit, the pivot point is going to be here. So all the clockwise torques is just this mg multiplied by the distance between it, and that's going to be about 4 meters here. So clockwise is going to have RF sine theta is equal to RF sine theta. So on the left hand side clockwise, we're going to have 4 times the force is going to be 3200 mg times 9.8. sine theta is just going to go to 1 because it's acting perpendicular to the arm, and R in this case is going to be 6 times your tension times your sine theta, which in this case is going to be sine 40. So from here you just go, yep, okay, get it out, yep, T equals 4 times 300 times 9.8 over 6 times sine 40. Put that in your calculator, you should get 3.26 times 10 to the 4 newtons. So the marks will be probably identifying the correct way of doing it. You might get a mark for this, definitely a mark for this working, and a mark for the final answer. Alright, what we got? Okay, pretty straightforward question here about drawing your field lines. Use your right hand rule so it's coming out from the page, so your thumb should be sticking out like that. If that's the case, you're going to have your field lines coming around like so. And the same thing for this one. Now, again, the direction's one thing, but then you also need to make sure that you... Oh, have I done a good job of it? That's the question. The field lines all need to be further and further away from each other to demonstrate that the strength of that field is getting slightly less and less. I'm sure that when you did it in your exam, you did it much better than me. So you're marking the right direction, I suppose, and the field lines away from each other, and I'm sure being circular. The question that I need to answer here is that are they attracted towards each other or repelled from each other? If we extend these out, you notice that if this keeps coming around, it actually works with this guy, so you could end up with a huge field around them like so. And the rule of thumb that I always use is if this sort of thing can in fact happen, then you're going to have attraction. So the next mark will be attraction. For part B, it's talking about a magnet moving into a solenoid. The first thing you want to work out is, okay, what is a solenoid going to create? So if you've got your hands, it's coming out of the page, this is going into the page, so it's going to be curling around like that. There you go. So you know that your north pole is going to be here, and your south pole is going to be here. Now, the movement that this magnet needs to have is in a way that this should oppose that change, which is why the magnet must be moving to the right. Because if the magnet is moving to the right, then this is going to generate a south pole here to try and stop that from happening, or repel it away through Lenz's law. So there's the answer. Part C, show the path that this positively charged particle will take. So your positively charged particle, your field lines coming out, positively charged is going this way. I'm trying to do the right hand rule under the camera, so it's going to be going this way. So it's going to be pushed to the right, and it's going to keep moving around. So it's going to keep on having a force directed to its right, which means it's going to go clockwise. Okay, these are pretty straightforward calculations. So what is the wavelength of the radiation emitted? You got this frequency there, so start with this guy. It's asking what the wavelength. So your wavelength is going to be equal to V on F. It's going to be equal to 3 times 10 to the 8 over 50. And what you should end up with is 6.00 times 10 to the power of 6 meters. And what is the energy of a photon with this wavelength? So now you're talking about photons, or quanta. This is this equation here. Again, nice and easy. 6.63 times 10 to the negative 34 times 50. And you should end up with 3.32 times 10 to the negative 32 joules. Cool. Yeah, so question 6 I thought was a little bit curly. I didn't really like it, so I've just got the solution here. So it's basically talking about the two postulates of special relativity. Most exams just ask you what they are. This one's saying what they are, and it's asking you what the contradiction is between them. So the answer key that Pearson puts out, it's reasonable. I just wouldn't have really thought of it myself. It's basically saying if the laws of physics are equivalent, like they're supposed to be, then the speed of any object should be different in different frames of reference. However, and that is the case. However, the speed of light isn't. So that contradicts the first postulate. And then it says, how can we accept this? And that is done using time dilation and length contraction. But again, yeah, I'm not sure whether it's the best question. Alright, so this question is nicely scaffolded for us. It's just asking whether this decay of the muon is possible. If you just want to do the lepton numbers, here you've got your 1, that's going to go to a 1, and your electron neutrino are the 1, so that is not possible. So 1 cannot equal 2, so therefore lepton number is not conserved. So it's not possible. This second question is where it gets a little bit hairy. At first, when I read the question, I thought it was going to ask me. It was asking me for a specific example, but it looks like it's been reviewed, and they're saying you're not required to identify a specific set of leptons or antileptons, but a general statement, which is kind of strange. But all it's really actually asking you to do is to say, okay, well, if you have a muon that is going to decay, then that means the lepton number after the decay must equal 1, right? Because before the decay it's going to be equal to 1. So for that to equal 1, and if it's going to 3 other leptons, that means it's saying leptons or antileptons. It's saying basically you need to say that it's going to be 2 leptons and 1 antilepton. The reason for that is you're going to have -1, -1 plus 1, and that's going to be equal to positive 1's positive 1, -1, and that's going to be equal to positive 1, which is what you need. Again, another really weird question. Not sure if that would be in a waste. Alright, so for question 8, it's asking basically when you turn a motor into a generator, how would that, in this example, slow down an electric train? So there's 5 points that you need to point out here. I've written them down already, so I don't have to write them in front of you. So the coil rotates in a magnetic field because you've made the motor turn. That coil is turning, and now you're switching it off. So you're turning off this the current to that coil. So now the coil is just freely rotating in that magnetic field. That coil will experience the changing flux because it is rotating, and that will induce a current in that coil. And that current in the coil, according to Lenz's law, I should probably write that in there. That should be down here. And that magnetic field opposes the motion that actually induced it. And when you have these two magnetic fields that are opposing each other, one from the wheels and one from the permanent magnet, or if it is a permanent magnet or however it's put together, that will slow the rotation of the wheels. So there's 5 marks, you can get them out that way. Yeah, so question 9 is a bit of a weird one as well. It's pretty straightforward, but the way they've asked is weird. So they've said here, towards the end of the question, that the solenoid is producing a magnetic field inside the solenoid with a flux density blah blah blah, but it's to the right. So your B vector is going to be going this way. If your current is running from P to Q, then what you'd expect is, like I've written there, a downwards force using your right hand rule. So you got your thumb's the current, and your B's the vector, so it's going to be pushing downwards. But again, this is a three-dimensional diagram too, so they're sort of taking a risk by asking you this way. But the big concern is, what is the magnitude of this force on the long side P? On the side PQ, you would just say F equals IL B, and what you would get is 5 times 10 to the -3 newtons. But it's not asking that. It's not asking what the force is on this arm. It's asking what is it on the long side. And since the current on the long side is running parallel to the field, the answer is just a big fat 0. But that 3 marks is confusing, and if you look at the solutions, they are giving this answer. But I'm fairly certain that's incorrect. Alright, question 10. The first one's just asking about why do electrons change direction in a magnetic field. We all know they do, but it's asking how would you articulate that answer. So you can say moving electrons, they create their own magnetic field, and then that field will interact with an external field, so you'd have the electrons will therefore experience a force and change direction. The next part of the question is, if an electron accelerator have 2.5 giga-electron volts, if it has 0.1% of its energy converted, what is the wavelength of the light? Okay, so the first thing you want to figure out is, what is this 0.1% of energy? So 0.1 0.01%. You want to multiply that by, what is it, 2.5 giga, so it's times the 10 negative 9, I think. No, 999, what are you doing? And that's in electron volts, so now you want it in joules. Put that in your calculator, I did earlier. You should get 4 times 10 to the negative 14 joules. Right, so that's how much energy you have. It's asking what the wavelength of that light would be. So if you have E equals HF, which is equal to HC on lambda, therefore your lambda is going to be equal to HC on E, which is going to be equal to 6.63 times 10 to the negative 34. Divide that by 4 times 10 to the negative 14. Put that in your calculator, which I did earlier, and you should get 4.97 times 10 to the negative 12 meters. Alright, question 11. What is the wavelength of an electron accelerated to 0.85 of the speed of light? 0.85 c. Alright, okay, so this is pretty much demanding that you include relativistic effects. So it's asking for the wavelength of an electron that's travelling at a velocity. So you're going to be using the de Broglie wavelength. Your momentum is going to be in the mv over, what is it, square root of 1 take v squared over c squared. Okay, so let's work out that momentum first. Your mass, velocity, over the square root 1 take. Now you're going to have 0.85 c squared divided by c squared, so that's just going to end up being 0.85 squared. If you put that into your calculator, what you should end up with is 4.41 times 10 to the negative 22 kilograms meters per second. And now you can pop that into your de Broglie wavelength equation. Whoops. So negative 22 and 1.50 times 10 to the negative 12 meters. There you are. Alright, so we've got an energy diagram for hydrogen, but we'll get to that later. What it's asking here is that satellite is measuring radiation with the wavelength of this, and then it's asking between which of these energy levels does that correspond to. So it's pretty straightforward. You work out how much energy you have first, right? So you have E equals HF, so you got HC on lambda. So you're going to go through 6.6, what are you doing? 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over 9.76 10 to the negative 8. Put that in your calculator and you end up with 2.037 times 10 to the negative 18 joules. Now these energy levels are in electron volts, so to get this in electron volts, I'm just going to divide that by 1.6 times 10 to the negative 19. I've done that already, and I end up with 12.74 electron volts. So if this is the number I'm looking for, looking back at the diagram, I want an energy change of 12.74. This makes it nice and easy for me, now that it's not in the negative values, it's all positive, so it starts at 0. So I can see the closest I can get to is there, 12.75. Now it's not saying it's exactly 12.74, it's saying it records a wavelength, so you can allow for a bit of discrepancy in this question. So the answer in this case would be between E4 to E1. Alright, so question 13, it's asking me to draw a graph. It's given me AC generator output, it's giving me 25 Hertz, so the first thing you want to do if you're going to graph that is work out what the period's going to be. So I'm just going to work it out here at the top. Period's going to be 1 on F, 1 on 25, so it should be 0.04. seconds, and then it's got so it's basically saying that RMS voltage is going to be 85 volts. So we know the factor's going to be root 2. We're going from RMS to peak, which means it's going to go increase, so you just know that V peak is going to be to 85 times square root of 2, which end up getting is 120 volts. So bringing that down to the graph, the important thing is that you just show a sinusoidal wave, and this is your period there, and there's your volts. You can write EMF here. Oh, there it is, EMF in volts. Time in seconds, and just mark this point here as 0.04, 02, and the EMF is going to be 120 there, and here is going to be negative 120 there. And if you've done that, you should be showing that you know how it all works. Okay, we're looking at section 2 now. The first question is pretty straightforward. You got a school athletics competition, someone throws a javelin, so you can see they've got a trajectory with an angle and a speed, I suppose. So what you want to do is you want to turn this into two different components. You have a horizontal velocity component and a vertical velocity component. So to do that, what we're looking at having here is just draw your triangle. I'll just draw it here. It's not very good with the lines, but we'll see what happens. So you got 20 meters a second. So along this way is your your horizontal. So in this case it's going to be equal to, if this is your angle 38, so it's going to be 20 cos 38, and your vertical goes upwards, it's going to be sine 38. This is the one we're interested in because we're looking at its vertical velocity at this point. So if you put that in your calculator, you should get 12.3 meters per second. Alright, so to solve this, it's asking you what's the maximum height reached by the javelin. So in which case we want to find out when is the velocity in the vertical direction going to be equal to 0. So to do that, we can use v squared equals u squared plus 2as. So if we have something like that, then we can immediately figure out that we can find s. We're trying to find s, so s in this case is going to end up being u squared over negative 2a. Doesn't really matter in this case because u and a are acting in opposite directions, so that negative is going to cancel out. Well, it's actually irrelevant. But if you put this in your calculator, you end up getting 12.3 squared over 2 times 9.8, and you get 7.73 meters. That's not the answer yet because it's saying what is the maximum height above the ground. So on top of that, you've got to add that. Look at the diagram, just 2.2 meters. Oops. And you end up getting 9.94 meters above the ground. This part B is what I would look at as being your classic projectile motion part of the question. So now it's asking how far horizontally from its point of release has the javelin landed. So just to recap on what we had a javelin that was 2.2 meters above the ground, and it's been shot and it's landing about there, and it's asking us what is this distance. That's SH. Alright, so to figure this out, let's just look at what we need to first do is find out what the time of flight is. So, flight time. Now, you'll find some solutions, even the Pearson solutions for this exam, they break it into two parts, which is just a waste of time, there's no need. So, what is the vertical distance? So we want to work in the vertical domain. Vertical distance in this case, I'm saying downwards is negative. You can say upwards is negative, it doesn't really matter. So I'm saying that S is going to be negative 2.2 meters. I'm saying that acceleration is negative 9.8 meters per second. And I'm saying that the initial velocity from our previous question is 12.3 meters per second. And that was done just using 20 sine, sorry, what was it? 20 sine 38. Okay, so we're stuck with this, and now we can chuck that into our equation of motion. S equals ut plus a half at squared. So if we put all of our variables into this now, so S in this case is negative 2.2, that's going to be equal to 12.3 t plus, sorry, is that still good? No, it's going to be negative half a, so take 4.9 t squared. Okay, so what I'm going to do with this is I'm going to put it in the form of a quadratic, so that way I can solve negative 4.9 t squared, take 12.3 t, this goes on the other side, so it's going to be plus, so that should be plus there as well, plus 2.2 equals 0. So chuck that in your calculator and you'll get two numbers. One will be negative, and that represents mathematically where this is a root here. So that's going to be a negative number, but then you have another value which represents this point in time here. And on my calculator I got 2.68 seconds. Right, so that is the time that it spends in the air. So now what I want to do is I want to talk about finding out what this horizontal distance is, and that's easy. That's just S equals VT. Now that I know what T is, I can just solve it pretty straightforward. So S equals 2.68 T times and the velocity in this case, which is going to be 20 cos 38, and I should end up with 42.2 meters. And there's your answer. Okay, so for part C, it's a question that's worth 5 marks, but I'm not sure that it should be. But it's asking how much kinetic energy does the javelin have when it strikes the ground at the end of its flight. So the important thing to understand is that the energy at the start needs to equal the total amount of energy at the end, right? So at the start, you have energy in the form of kinetic energy plus the 2 meters above the ground, so mgh, 2.2 meters above the ground. And at the end, you've lost that potential energy. That's turned into kinetic energy. So that's just, so at the end, you should just end up with EK. So the marking key says you just need to show an appreciation for the fact that this kinetic energy is just equal to the amount of kinetic energy you have at the start plus its height. So if you just put those numbers in, you'll end up just getting put the numbers in, 0.85 times 20 squared plus 0.85 times 9.8 times the height is 2.2, and what you end up with is 188 joules. And that's how easy it is. Alright, question 15. You've got an airplane that's doing a horizontal loop. Bring it down. You can see it's going to ask some questions about banked angles soon, but the first question is really straightforward. So it gives you, tells you that it's taken 20 seconds for it to complete one full circle. So that 20 seconds is your t, your period, and your velocity is 120 meters per second. So knowing your circular motion, you know the velocity of an object going in a circle is equal to the circumference, or 2 pi r, divided by the time taken to reach that circumference, something like that. So rearrange that, you end up getting r is equal to v period over 2 pi, and substitute those values in. So velocity is 120 times 20 over 2 pi, and you should get 382 meters. Okay, part B, we can start talking about banked angles. What we've got here is we've got a situation where you've got a gravitational force, it's also creating a lift force, and then the final product of that, if it's not made clear enough, is that you have a net force that is your centripetal force. So the first thing that I would do in this case is I'd actually draw the free body diagram. Sorry, there's a free body diagram. I actually draw a vector diagram. So your gravitational force is this way with the mg, and you have your lift force, and that is going to be creating your centripetal force. Now, thanks to similar triangles, I know that this angle here is going to be 60 degrees. So with this triangle I can solve to find out what this force is here. So if I know that cos 60 is going to equal adjacent over hypotenuse, I can now say that that lift force is just going to be equal to 60, so 5,000 times 9.8 over cos 60, and I end up with a number of 9.8 times 10 to the 4 newtons. There we go. Alright, part C. It's just asking us, okay, if we have a pilot inside that cockpit, his apparent weight's 3,000 newtons. That's not really relevant at this point, but he is doing an upward arc. So what that means is that forces acting on this guy, he has downward force, that's the force due to gravity, and he has an upward force, and that is your force, your normal force, and that's what's creating that apparent weight. So question saying draw and label the direction and magnitude of the forces as well. So FG, you're going to want to end up with a number of, now right at the start of the question it's saying his mass is 75 kilograms, so 75 times 9.8, you'll end up with 735 newtons, and the normal force has been given to you already, 3,000 newtons. Part D follows on from above, where it's saying, okay, well, if the aeroplane is flying at a constant speed of 80 meters a second at point A, which is this point that I'm describing up here, what would be the radius of the arc flown? So first thing you want to do here is figure out what the actual centripetal force is that's keeping this guy in a circle. So you know that because it's telling you that these are only two forces acting on it. So your centripetal force is just going to be your normal force subtract the gravitational force. So it's the first step. So I'm going to say it's Fn subtract Fg, so it's going to be 3,000, take 735, and that's going to end up being 2265 newtons. So this is your centripetal force that you're working with. And you know that centripetal force is going to be equal to mv squared on r. Knowing that, you can rearrange that to find out what is it asking, what is the radius. So r is going to be equal to mv squared on fc. So you put the numbers in. 75 is the mass of this guy. So we're not talking about we can talk about the plane, but we've been given the normal force on the person, so we can just use that information. 75 times 80 squared divided by the centripetal force, 2265. You do that and you end up with 212 newtons. And finally, the last question is talking about weightlessness. At what speed would the airplane need to fly? So it's pretty straightforward, sort of bucket whizzing around upside down sort of thing. The first thing you need to do is you need to point out that for weightlessness, you need the centripetal force to be provided only by gravity. And you can substitute those numbers in now. mv squared on r is going to be equal to mg. m's cancel. So you end up with v squared. Of course, I'm doing a pretty long way here, but whatever. It's asking for what speed. So it's asking for v squared. Therefore, your v squared is going to be equal to rg, which is going to be 9.8 times 400. The 400 comes from the first diagram that you saw. It's not 80. And you do that, you get 3,920. Therefore, your velocity is going to be equal to 62.6 meters per second. Okay, so for question 6, it's your standard satellite question. Satellite is placed in orbit 600 kilometers above the Earth's surface, so immediately you need to realize that this is above the Earth's surface, so its radius, which is relative to the center of the Earth, is actually going to end up being the radius of the Earth plus your 600 kilometers. And if you do that, you should end up with 6.97 times 10 to the 6 meters. So it's asking what orbital velocity must this satellite have. So to do that, you can solve using your centripetal force, equating that to your gravitational force. I use big M, little m. I'm not sure what they have in the formula sheet anymore, to be honest. Over r squared, and if you have that, what you should end up with is V is going to be equal to the square root of gm on r. So what that ends up being, I'm going to try and draw this out nice and big, is 6.67 times 10 to the negative 11 times 5.97 times 10 to the 20, is that 24? And that is over the new radius that you've calculated, 7 times 10 to the 6, and you should end up getting, where are we, 7.56 times 10 to the 3 meters per second. Now the bad thing about this is that if you got this wrong, then you're going to get pretty much the rest of this question incorrect. But I'm sure a good marker would be nice to you and give you some carry through or follow through marks. But the next question is asking for the period of orbit of this satellite. So going back to the equation we've already used before, it's 2 pi r on your period. So your period's just going to be equal to your 2 pi r on your velocity. And we've already got your velocity, so it's just going to be 2 pi times 10 to the 6 over the actual number up here is 7558. So you can use a higher precision number, and you should end up getting 5.80 times 10 to the 3 seconds. Next one is, what acceleration due to the Earth's gravitational field does the satellite experience? I did this differently to the way the Pearson answers suggest you do it, mainly because it keeps the precision, and this way it makes more sense to me. If you have the gravitational force as this guy, then you also know that F equals ma, so gravitational acceleration can be written as basically this divided by your m value, so gm on r squared. That might even be in the formula sheet, I'm not sure. So you end up being 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 over 6.97 times 10 to the 6 squared. Put that in your calculator, and you should end up with 8.20 meters per second squared. Alright, nearly there. Why do objects in the satellite experience weightlessness? I don't like this because experience weightlessness, it's talking about apparent weight. It's not saying that those objects are weightless, which is why that question is worded in a way that could be a little bit controversial. So it's basically asking, why would an object in there have an apparent weight of 0 or something along those lines? So there's 2 marks towards it, but the first thing you want to say is that objects inside fall at the same rate as satellite, or they have the same acceleration as the satellite. And you also probably want to point out that the apparent weight, or the experience of weightlessness, apparent weight, depends on a reaction force. So since there's no reaction force, there is no apparent weight. Basically, an object isn't being pressed into something by gravity, so it has an apparent weight of 0. Next question is, orbiting satellites are fitted with small propulsion devices to assist in stabilizing their orbit. Without these devices, they are likely to slow. Explain why they may slow and what would happen if they did. This is a weird question because tons of things can slow the orbit. So you could always talk about other gravitational influences, so the moon and other planetary systems. You can talk about drag, if there is a little bit of atmosphere, depending on its altitude. You could talk about space junk, if it collides with something, I don't know. There's a few different options you can have here. But there's your first mark. The second mark says explain what would happen if they did effectively fall to the Earth, or more technically spiral into the Earth. There we go, you're done. Okay, so for question 17, you got yourself a typical graphing question, but if you've done any graphing questions in a physics exam before, you know that they will typically give you something much easier and better and more precise to work on than just, you know, two axes. And there's not even much room to write anything here, so you don't expect this sort of thing in your exam. So the first question is just to plot a graph of kinetic energy against frequency on the axes below. So I've already done that for you here. It's pretty straightforward. I did this without a ruler, sort of just did it by freehand just to see how accurate I could get it without it. Everything came out pretty good, nice straight line. So the first question about the graph that it's asking you is to use the data from the graph to determine the threshold frequency for the metal. Now the answer you need to get full marks is between 1 and 1.3 times 10 to the 15 hertz. And you can see here that with my, you know, hand-drawn version of this graph, I actually got within that range, so it shouldn't be too difficult for you to reach that. But if you didn't get that, you still would have got a mark if you chose this point and you make it clear that it was this point. So recognizing this point here is your threshold frequency, or the frequency at which you start emitting photoelectrons. That's your first step. So the second question is third question is use the data from the graph to determine the work function for the metal. Now the reason I've written this up here is this is effectively what you are graphing. So the work function represents your y-intercept, or the negatively y-intercept. So here is where you need to show your value from. So if you actually showed that you chose your value from here, you got yourself 1 mark. But to get the actual, to get the full marks, the 2 marks out of it, you would have needed to get, if I can find it, where is it? 7.7. They would have accepted anywhere between 7 and 8 times 10 to the negative 19 joules. Is what is typical there. Determine the slope of the line. It's a pretty straightforward thing to do. You just do your rise over run, and what you'll end up with is essentially what you'd expect: 6.63 times 10 to the negative 34. Why? Because again, you're drawing this graph, so what you should be getting is something that's fairly close to Planck's constant. The next questions are a little bit strange. The researcher carries out the same experiment to determine the threshold frequency and work function for a second metal, and graphs the kinetic energy against frequency. Predict the slope of the line for this second metal. If I was the examiner, I would have said something like, you know, the metal, it's a different metal, or and explain why it's a different metal. It takes something to sort of throw you off. But the obvious answer here is that the slope is going to be the same because Planck's constant. It's Planck's constant. So you want to say that 6.63 times 10 to the negative 34. And here explain what effect studied in this experiment provides evidence for. So what the effect that we're studying provides evidence for in respect to electromagnetic radiation. I guess the most important thing is this is the particle nature of light. And you can talk about how from that point on energy is quantized. Discrete packets of energy. I think those sorts of words, I think, is what they're interested in reading. But yeah, that's that one. Okay, question 18. Space probe is spent. Okay, so we're looking at the relativity question here. So you've got a space probe being travelling at 0.82 times the speed of light, and it's carrying an atomic clock, and the distance that it's travelling is 24.6 light years from Earth. So the first question is, how long will the journey take as measured by a clock on Earth? So in other words, how long will it take according to someone on Earth? Well, it would just be that 24.6 light years. So if you just, you know, this equals VT, so you know that the time is going to be equal to S on V. So because we've got light years and we have this in C, it makes the determining it really easy. 24.6 C years divided by 0.820 C. Put that in your calculator and you'll just get 30 years. part B is how long will the journey take as measured by a clock on the probe. So this is not a tricky question, but the wording's a little bit funny. It's basically asking how long will the journey take. If you're on Earth and you're looking, there's two ways you could look at it. If you're on Earth and you're looking at the clock that's actually on the probe, what will it read? And you know that because that clock is going to be going slower, it will read a number that is less than the 30 years that you got there. Another way you could look at it is that if you're actually on board the probe and you're looking at the clock, you're no longer travelling at this distance up here, you're now travelling at a much shorter distance because of length contraction. So again, it'll take less time. So once you know that the number needs to go down, in this case, you know that you can just work it out by multiplying it by that gamma factor, which is 1 take 0.82, I think, yeah, squared. If you put that in your calculator, you'll end up with 17.2 years. Following on from part B, now we're looking at C. It's asking us from the probe's frame of reference, what is the distance travelled? So we are now actually going to be applying length contraction. That's pretty straightforward as well. And but then you should get 14.1 light years. Again, you know that it's going to be smaller, so you know what you need to do with that factor. Oh, sorry, light years. Okay, so now looking at D, it's asking you from the space probe's frame of reference what velocity is it travelling. This is a strange one because I know that some of my students thought the answer would be 0, but because you're not supposed to be able to know how fast you're travelling unless you look outside. And I think this question doesn't make that clear enough. But if you could see what's happening outside, how fast would that probe think it's travelling according to its own frame of reference? The easiest way to look at that is say, well, if someone on Earth is seeing that it's travelling at 0.820 c, then you flip the reference point and you're inside the probe, it's going to be the exact same answer. It's going to be 0.820 c. The other way you can look at it is you can say, well, velocity is distance over time. You now know up here, you've figured out what that distance is, 14.1. And you also now know what the clock's reading on top of that, on board that ship. And you do that, you'll still get 0.820 c. Let's write that a little bit neater. Because that one there will be light years, so C years. And this will be in years. Okay. Alright, and now we're finishing off with your relative velocity question. First thing you want to do is, the tip that I always give is you want to find out what the moving reference frame is, and that's going to be your V. So V is the reference frame that is moving. So you've got a probe, it's launching a smaller probe at a speed of blah blah blah. So this probe, we know the speed of this probe, which means this is the moving reference frame. So V, which is the probe, is going to be 0.820 c. And what else have you been given? You've been given the speed of 0.65 c relative to that probe. So you've been given U dash. So U dash is always what the velocity is within this moving reference frame, which means you want to find out what U is. So your equation is from your formula sheet, V plus U over, U dash, sorry, over, I'll try to write this a little bit neater, V dash over C. Now because all of these are in C, this actually simplifies out quite nicely. It's in at 0.820 plus 0.65 over 1 plus 0.82 times 0.65. And that whole thing is a C out the front, or out the back. And what you should get is 0.959c. And now your last question. What velocity will the signals travel from the probe's frame of reference? So you know the signals are the speed of light, you know the signal is the speed of light. The question is, explain your answer. You can say the speed light is an absolute constant. Or you can say the speed of light is the same in all frame reference frames. There's a few ways you could word that. Essentially what you're doing is you're reciting one of the postulates of special relativity, but that's it. Okay, and this is the last question about section 2. So you've got pretty straightforward electron gun here. You have electrons that are being attracted to this anode, and they get accelerated across this pathway before they continue through, apparently unaffected. But what the question's asking you at the moment is, what speed will the electrons exit the electron gun? So this question, it's a little bit strange because it's saying what speed will the electrons exit the gun, and you need to make the assumption here, or the clear assumption, that they are only accelerating between the cathode and anode and they're not losing any energy here. And if that's the case, you need to look at the work done on one of those charges as work equals QV. Now that work done is going to be the equivalent to a change in kinetic energy, and that's going to be your half mv squared. So once you've got that out, you end up just with QV is going to be equal to a half mv squared. And it's asking you what V is, so that simplifies down to, where are we? If you want, you can either fill it in, it's up to you. We'll just go with V over here, V squared is going to be equal to QV over a half M, or you could just have 2QV over M, 2 times charge of an electron, and the voltage we're looking at is given to you as 16 kilovolts. And you can divide that by the mass of an electron, 1811 times, here, 10 to the power of negative 31. I haven't got that answer, but V is the square root of this. I did put that in my calculator, and that answer should be 7.5 times 10 to the 7 meters per second. There we go. Question B is asking, well, the first thing, it's a bit sneaky here, is it changes the speed, and that matters in the next question. It's pretty easy to get tripped up from that. But you have this electron that's being fired, and it's now changing direction, and the first question is just asking, what is the direction of the magnetic field that causes the electrons to follow this path? So with my right hand, I like to think of this side of my right hand, rather than the thumb being the positive charge, this side of my right hand being the negative charge, and it's obviously experiencing a force that is going downwards, and for me to do that without hitting the camera, I end up showing that the field is going into the page. So I should end up with this sort of thing happening. So moving into the page. Alright, last page was section 2. One thing I did notice, and you'll figure out, is that there's really not much space in the whole exam, but this part especially. What is the magnitude of the force acting on the electrons as they travel through the magnetic field? So it's a pretty straightforward equation. F equals QVB. The issue is that on the other page they changed the speed to 1.5 times 10 to the 5 meters a second. So it's just going to be 1.6 times 10 to the 19 times 1.5 times 10 to the 5 times the magnetic field, which is 20 times 10 to the negative 3. What you should end up getting is 4.8 times 10 to the negative 16 newtons. Pretty easy. The next question is asking, what is the radius of the arc of the circle that electrons flow via the magnetic field? So this can be derived. It used to have to be derived where you have mv squared on r, which is the centripetal force. You equate that with the force on the particle due to the magnetic field, and once you've got that, you'll end up with mv on r is equal to qb, and then from there you'll end up with r is equal to mv. I'll put up here mv on qb, and I think this is now your data sheet. So at the end of the day, it's a really easy question if you've already got that formula. 31 times 1.5 times 10 to the 5, and your charge is 1.6 times 10 to the negative 19 times 20 10 to the negative 3. And the answer you should end up with is 4.27 times 10 to the negative 5 meters. And there's your answer there. And you notice straight away here that for question E, there is absolutely no space for you to figure out the question. But you should be able to just write it in here. The product of the low energy collision between these particles, so you're having an electron colliding with a positron, and all of that energy essentially is going to be converted into light energy in the form of 2 photons. So the important thing that this doesn't do, but for the conservation of momentum, the photons just have to be the same amount of energy, but you just want to find out how much energy there is first using that, and you should end up getting, I'm not going to put the equation because I'm out of space, but you should get 1.64 times 10 to the negative 13 joules. But that's for the whole lot, so that's how much both those particles are worth. If that's divided up amongst 2 photons, you should end up getting, 8.2 times 10 to the negative 14 joules per photon. There we go. Okay, so to produce particles heavier than themselves, electron and positron need to collide at higher kinetic energies. When they collide at low energy, they produce only 2 or more photons. Explain why high energies are needed for production of particles heavier than themselves. And this is interesting. Both of these next questions I was a little bit unsure about, I suppose. But at the end of the day, you can pull out mass energy equivalents and talk about, well, if you got more energy, you'd be able to get more mass out of it, I suppose. But the answer in the answer key is on the same realm, is you have a higher momentum in the collision, and that needs to be conserved. But this is where the leap comes, is if you have these things, then you end up with a higher chance to produce heavy particles, more massive particles rather. But as far as I know, you'd only really understand or know that if you're a particle physicist, or if you dive deeper into the curriculum than you need to. But this is a higher order question, I suppose. The next question is another consequence of high energy collisions is greater resolution to study finer structures. Now, the reason I like this question is, I know what resolution means, but you may not if you're a Year 12 physics student. Study finer structures, which means to study finer structures, and I think this was in Year 11 or it might have been Year 12. You need to know that to do that you need a shorter wavelength, or you need a higher frequency to get to those through those structures. So again, you have high energy, more importantly, high momentum. And what you really need to pull out of this is, if you're studying finer structures using these particles, like high, I think a better way to look at this would have been talking about the speed of, say, neutrons, for example, how fast a neutron needs to be and what it can observe, rather than looking at collisions. It's a little bit strange. But if you do that, you can talk about how the wavelength is related to Planck's constant over the momentum. So the more momentum, you get shorter wavelength. Which means you'll be able to get high resolution. But again, I don't like the idea of talking about collisions. They should just be talking about particle speeds. But yeah, and that's it. That's the end of section 2.